Okay, so what I just handed out was the priorities of the functional groups, which is in your folder under Wednesdays. In Wednesdays, it's there. I'm going to open it up from full screen. So this now is going to come into play today, as well as with the other functional groups that we're going to name. This gives you the priorities of the functional groups. And what you see at the bottom here is the idea that halogens and alkyl groups and OR groups, which were the ethers or alkoxy groups for today's reading, they're all they're second at the bottom, but really they're at the bottom of the list. So they don't have any priority other than their alphabetization. So an alkoxy group is no different than methyl, ethyl, propyl. It doesn't have any kind of special priority. When we get to a triple bond or we get to a double bond, now we're starting to have priority. And I reconciled the issue with the book and this chart on how sometimes double bonds and triple bonds, there's actually no rule about whether they switch or not. So I'm going to talk about that in a moment. But now as we move up the chart with our functional groups, on this chart, and you'll get to use this chart for your homeworks and exams, and we may add some things onto this, like expand out this, what is this CHO, what does that look like? Why is there a C in brackets? I'm not quite sure, but what's the CHO look like? What's the C double bond O look like? So we can write the functional groups a little bit more on this chart, but as we move up the chart, those groups have a higher priority. And there is no rhyme or reason for this. Like when we talk about Kahn-Ingold pre-log sequence rules, you would think that those would be a perfect set of rules to create this chart. That's not how they did it. So that's why you need this chart, because it would be, there's no sense in memorizing it, because you would always go to this chart if you have more than one functional group. So if you do have, Ty, if you want to grab. So if you have the numbering scheme, or as you're looking at a molecule that has more than one functional group, you have to decide who has priority, because whoever has priority, then you number from the end closest to that functional group, except double and triple bonds that I'll go into in a minute. And then that name always comes at the end. That suffix is always at the end of the name. So that's why you need this chart in order to, number one, in order to remember what the groups are called. But then secondly, who has priority, how that dictates the numbering scheme, and then more importantly, how you write the name with that higher priority last. So that's how we're going to use this chart. So that's why you have a copy of it, and we're going to use it. I'll refer back and forth to it as we go along. Now there are two columns here. Initially, we're going to deal with the third column. The second column, I'll show you how it works as we go through the different names. Okay. And with alcohols, that's a perfect way to show the difference between the second column and the third column. Okay. So we'll learn how to use this chart as we go through the different naming. Right, but this is I just took this from the book. Right. Now, the triple bonds and the double bonds. Apparently their IUPAC did decide to carve out exceptions. So I went to the blue book. The blue book is I went to the online edition of the blue book. I'm more confused now than I was beginning, because there's a blue book online, and then there's the latest edition of the blue book that's not online, but it's like $2,000 to buy the book, which I'm not doing. So until they put it online, I'm not dealing with that. with the new revisions. And so some of this stuff, for instance, here where it says 2-hexene, they've revised 2-hexene to be hex 2-ene. So that must come in the book that's not online. But everything else appears to be the same. So reading this is like reading the Ohio Revised Code. And you have to be a lawyer almost to figure this stuff out. But the stuff I put this in today's folder if you're curious. So when they say, for instance, the unsaturated branched acyclic hydrocarbons, that means double and triple bonds. Saturated and unsaturated. Saturated means you have maximum hydrogens per carbon. Every time you put a double bond in place, you lose 2 hydrogens. So if you think about CH3CH3, that's 6 hydrogens, 2 carbons. If I make that a CH2CH2 with a double bond, it's now C2H4. So that's unsaturated when you have a double or a triple bond. So if you hear about unsaturated fats and oils in nutrition, that means that your molecule has double bonds in it. Whereas if it's saturated, it has alkanes. So, and we'll talk more about that, that term. But that's what it means. Unsaturated, unbranched, acyclic hydrocarbons. Bless you. So, double or triple bond, no branches, no rings, hydrocarbons. And the chain is numbered, and then there's a little red arrow, I think, that goes down here to give the lowest possible numbers to the double bonds. That's if there's more than one double bond. If there's one double bond, you're numbering to give the double bond the lowest number. We already knew that. So the 2-hexene would be, this 2-hexene would be hex 2 in the new system. Now, when there's double and triple bonds in the molecule, the book is correct in terms of what IUPAC did. So for instance here, this molecule has a triple bond at carbon 1, triple bond 1, 2, 3, 4, 5. This is called it would be called pent 3-ene 1-ine. Because all we're doing is just switching this 3 inside. That's what the book uses as the new terminology. And like I said, I would have taken the page from the new terminology, except it's like 1,500 pounds to buy the book. And like I said, that's not happening. Number one, it's not on Amazon, so I can't get it, Prime. But that's a little bit above my budget for a naming book.
Why would it be ene before ein if, ene has higher priority?
So this is the issue, right? This is what I said. I don't know why the book is doing this. The book is doing this because IUPAC says you do that. So up here in yellow, it says that we call this an ene-ein, is what they say. So unsaturated, unbranched, acyclic hydrocarbons having both double and triple bonds are named by replacing the ending ane of the name with the corresponding saturated hydrocarbon ending in ene-ein. A diene-ein, a triene-ein, ene-diene, those di terms mean more than one double and triple bonds. That's all that means. That's why it's not in yellow. Numbers as low as possible are given to the double and triple bonds, even though this may at times give ein a lower number than ene. So in the book, they said number from the end closest to either the triple bond or the double bond, whichever one is closer to the end. That's what that statement means. So you're going to give the double and triple bonds the lowest possible numbers, and sometimes the Y and E will have a lower number than the E and E. So I think they're acknowledging the fact that the priority would normally be E and E, but on occasion it will be Y and E. So the example down here of the pent 3 ene, 1 ine. The triple bond is at the beginning of the chain, and so that's why they're giving the triple bond. Whereas what they should have done, well, they did that up here, right? They put in the hex 1,3-diene 5-ine. What they did was they basically gave the double bonds priority, because I could number this top chain from the left to right or right to left. What they did was they're going from they're going from right to left, because they're giving the double bonds priority over the triple bonds. So if there's a tie at the end, you give the double bond a priority over the triple bond because it's higher up on the chart. Now, why the YNE is at the end, this is the anomaly, because in every other case, the group that's higher on the chart will be at the end. But they said you do this with an ene-ine instead of an ine-ine. So all the rules in the book are up to date. Again, if you made a minor, if you flip those around, that would be sort of a minor error. So I'm not, because this is kind of, I don't know, this is different. So, and then anyway, they go through and talk about chains. So you're trying to draw the chain, the longest chain that contains all of the functional groups. And if there's a tie in that, you're going to choose the longer functional. You're going to choose the longer chain. Is kind of those different tiebreakers. So if the number of carbon atoms in the chain is equal, and the different chains are equal, that one containing the maximum number of double bonds is the one that you choose as the tiebreaker. So what the book's rules are correct, because IUPAC made these sort of anomalous rules. So in terms of a double or a triple bond, you're going to basically choose the longest chain that contains as many of the double and triple bonds as possible. If not, the problems I'll give you, you'll be able to have the chain contain everything. And then you number from the end closest to the first double or triple bond, but the YNE always comes last. Suffix, so as the last of the suffixes. And then they have some groups that they have given IUPAC names for. So these are alkyl groups, and they've given those their own IUPAC name, which come from sort of the common names. But I don't think we're going to have to go down that rabbit hole. So this is literally the rule book for naming, the blue book, the IUPAC blue book. And again, it could be written a little bit more common for the common chemist that doesn't really care all that much about naming until you actually have to name something. And there are programs that actually would give me the proper name. I think I have one on my computer, but I'm not sure what system it uses. If it uses the 3-pentene 1-ine, or whether it uses the pent 3-ene 1-ine. So again, if you're doing book problems, that's their system. That's the system you're using, which I believe is the newest one. So the book's correct. IUPAC just did something strange, as far as I'm concerned. They didn't ask me. I would do it differently. Again, their goal is to make sure everybody names everything the same. So hopefully that hasn't confused the issue more. But what's in the book is the way that we're gonna the way we number it. So what kinds of questions did you have on that, on Today's was ether, all the different functional groups. Ethers, alkyl halides. Olivia? The complex organic compounds. Multiple functional group. What kind of multiple functional groups would you like? Alkenes, alcohols. We can do an alkene and an alcohol first. We can do an alkene and an ether as well. So, and we'll do acyclic first. So in other words, no rings. Let's see. Let me start out something like this. I'll put a double bond there. I'll put a methyl group there. And I'll put an OH group there. That seems like it. And I can get myself into big trouble when I just start whipping out these names. So if I get myself in a tie-breaking situation that I don't know the true tie-breaking answer, we'll make something up. Longest continuous carbon chain that contains both the double bond and the carbon attached to the OH. That's going to be this one, right? Again, if I have more time, I can be more creative and hide the parent chain. Okay, how many is that? 1, 2, 3, 4, 5, 6, 7. So this is going to be a hept. Okay. Now in the chart, because the anomaly about starting at the end closest to the first substituent is only for double and triple bonds. Once we move past a double or triple bond up into the next higher levels, there is a distinctive high priority group. So OH is higher than double bond. So that means I am obligated to number from the end closest to the carbon with the OH. The OH takes precedence. Okay. Again, if they would have done this right, in my opinion, they would have always said the double bond takes precedence over the triple bond, but they left that little weenie language. Well, sometimes the triple bond can be. So once you get above the double and triple bonds, you have no choice. So we have no choice but the number 1, 2, 3, 4, 5, 6, and 7. So we have no choice but to number from the end closest the OH group because it is higher on your chart. Okay. If there was a tie, which actually there is in this case, if there was a tie between two groups of the same priority, then we would probably use the other group to break the tie. And then if there was a tie there, we probably then would go to the substituents and alphabetization like we do with alkanes. So in this case, what do I have? Now, I have one substituent, which is which group? The methyl. You might say, what about the OH? The OH is that higher priority functional group, the alcohol. So what we need to know is we need to know what are the suffixes then for a double bond. And the suffix for a double bond is ene. What is the suffix for an alcohol? It's OL. Okay. So in this case, the OH having the higher priority is going to come last in the name. Higher priority groups get two privileges. They get the numbering scheme favoring them, and they get the last name in the last part of the name. So this would be a hept 5-ene to all. Would be the parent name. Look. So again, taking a step back, if I'm translating that name into a structure, what would it mean? It would mean I have 7 carbons. I have a double bond between carbons 5 and 6, and an OH group attached to carbon 2. What's my substituent? A methyl group. And where is that methyl group located? So I've got a 3-methyl group, so now I'm up to 3-methyl hept 5-ene 2-all. There's one more thing I need. And that relates to a double bond. So is there a stereochemistry that I can assign to that double bond? Again, what I'm going to have to do is I'm going to have to put in the hydrogens there and there. And if I put those hydrogens in, what is the stereochemistry of that double bond? It's going to be trans. So this is going to be trans 3-methyl hept 5-ene 2-all. And it's trans because each of the carbons in the double bond here have one non-hydrogen group and one hydrogen group attached. And the 2 non-hydrogen groups never have to be equal or the same. In what if the cis one I would have written like this. So this would have been the cis 3-methyl hept 5-ene 2-all. Okay. And this methyl group is part of the longest chain. So that would have been the cis stereochemistry. If there's 3 non-hydrogen groups on the double bond, then we go into EZ territory, which we'll still hold off on here. Okay. So in the functional groups for today, bless you, the new ones ended up being, if I go to top hat here, in the functional groups for today of alkyl halides, ethers, and alcohols, in the chart, only the alcohols have a higher priority than the double and triple bonds. Actually, everything else has a lower priority. Okay. And is that what else? I mean, I can go from here and hit the big stuff, but but if there's something that, as you were reading through, I want to get to that first. Ethers. Do you want to do just a regular ether first? And the what? So let's do an ether with a double bond. So here's an ether with a double bond with a halogen. Now, hopefully you've seen with the halogens that we've treated halogens as if they were methyl ethyl groups. They had no special priority. And if you look at your chart, you'll see that the second from last groups include X, which are the halogens. So the halogens are second to last from the bottom. They have no priority other than their alphabetical position. But you'll notice that next to the halogens is also the OR groups. So what's funny about this is the OR groups have no priority either. They're just like methyl, ethyl, bromo, etc. But when we have an ether functional group, regardless of whether there's a double bond or a triple bond present, when we have an ether, what we have to do is we have to assign one side of the oxygen as the substituent and the other side of the oxygen as the parent chain that I'm going to use to name a number as the alkane, or in this case, as an alkene chain. And the rule for determining which side is which is totally based on the number of carbons. So in this case, I only have 1, 2, 3, 4 carbons, and down here I have more than 4 carbons. So that means that this group is going to be, that's going to be my parent chain. So that's going to be what I'm going to use to name a number, just like I've done all the problems before. And what it means now is that this group, this alkoxy group, is now going to become a substituent that's just like methyl, ethyl, or bromo. Only one issue here is that oxy group is going to be named, what comes before the oxy is, what is the IUPAC name of this alkyl group? What is the name of that alkyl group? Okay, I will accept that it is a butyl. It's going to be, it's going to be a butoxy group because that alkyl group is a butyl group because it's got a total of 4 carbons. What kind of butyl group is it? No, in order for it to be iso, there'd have to be a CH3, a CH, and another CH3, which there's not. So this would actually be a sec butoxy group because that is a sec butyl group. Why is it a sec butyl group? Because this is the butyl group where the attachment point is what kind of carbon? Secondary. So that's a sec butyl group, which makes this substituent, and I'll get rid of the box now. That entire group now is a sec butoxy group. And now it falls into the realm of, it's just another group. Okay. So when we're naming ethers, the first step is choose who's the parent group, parent chain, and choose who's the substituent. And that's based on the total number of carbons. The smaller number of carbons instantly becomes the substituent. Now for sec-butoxy, how am I alphabetizing? I'm alphabetizing on what letter? B. I'm alphabetizing on B. Why? Because whenever it's a hyphenated name, we ignore before the hyphen. What are hyphenated names? Tersh, sec. If it's iso, it's all one word, which means you alphabetize on the first letter. So the only power that the sec-butoxy group has, any priority that it might have, is simply because it starts with a B. Other than that, it has no priority. Okay? So that's kind of you'd think an ether would be higher priority than that, but it's not. Once you decide who's the parent and who's the substituent you just name it, and now we go with our normal rules.
So just because butoxy comes before bromine alphabetically, you number it in that direction?
No, we haven't numbered yet. And actually bromo would come before butoxy.
Oh, okay. What if, like, okay, no.
Now, well, maybe my psychic abilities are coming back. What about butoxy versus butyl? You know, then it's then it's an O versus a Y, and the O would win. So butoxy would beat butyl if I had like a butyl group, or if I had a sec-butyl or a tersh-butyl. So it's totally based on alphabetization. But now what do we need to do? Now we need to number, we found the parent chain, we found the longest continuous carbon chain. Right? And again, I'm treating this group, this circled alkoxy group, as just some other group. So here's my longest chain. Now, when I look at that longest chain, what do I see? I see that it has a double bond in it, so now I have to use the double bond rules for numbering. And so that means I have to number from the end closest to the double bond. So let's see, that's going to be 1, 2, 3, 4 that way, and 1, 2, 3, 4 that way. So we have a tie. That's okay, because how am I going to break this tie? Now I'm going to start looking at the substituents. So now the end closest to the first substituent, which is going to be, the first substituent is going to be the bromine versus the methyl group. Oh, nope. No, we have a tie there too, don't we? So just to recap, if you're like, I'm lost. We're numbering from the end closest to the double bond. If I number from left to right, it's 4. Right to left, it's 4. Tie. First substituent going from left to right is a butoxy group, sec-butoxy group. Going from right to left, it's a bromo group. So now it's alphabetization, who beats who. Bromo beats butoxy, so it's going to be 1, 2, 3, 4, and now it's going to be 5, 6, 7, and 8. So we numbered from the end closest to the double bond, tie. We then go number from the end closest to the first substituent, tie. We break the tie based on alphabetization. And bromo beats butoxy. If they would have been tied, the methyl group being 3 carbons in from the left would have won. But we didn't get there. Okay, so now I'm just numbering and going through the rules as if that butoxy group was a methyl group. What are my substituents? I've got a 2-bromo. I've got a what methyl? I've got a 6-methyl. I've got a 7 sec butoxy group. on an 8-carbon chain. So now we can go ahead and create our alphabetized list. So this would be 2-bromo, 7-sec butoxy, 6-methyl oct 4 ene. Now we've got to deal with the cis and trans after we get to that point. So then H and H, this is the trans stereoisomer. So it's trans 2-bromo, 7-sec butoxy, 6-methyl oct 4 ene. Makes sense? Doesn't make sense? So there were a couple of those. There were a couple of those problems. I think numbers 49 and 50. I think I had answers. I put answers on Piazza to those, so that I went through the same procedure. The first thing with ethers is choose a parent, choose a substituent. What else? And I kind of know where we can go from here, but what else? If we're going to do acyclics, we might as well do rings. How do the rules change as we go to higher priority groups with rings? This is where things get a little interesting. Not necessarily this one, but they can get interesting. So in this molecule, what I have is I have a cyclohex. I have a double bond and an OH group. So I look at my chart, which one of those two groups has a higher priority? The OH does, the alcohol. So that means that when we have rings that have no priority groups, no high priority groups, nothing but alphabetization, that's when we use our lowest total sum of substituent numbers rules to come up with the naming. So if you have a ring with halogens, alkyl groups, and now alkoxy groups, lowest total sum of substituent numbers. But the minute that I move to a double bond, note you can't put a triple bond in a ring because it's got to be linear. The ring has to be like 7 or 8 carbons large before a triple bond can exist and be linear. So that means if we just do cyclohexanes or cyclopentanes, triple bonds are out, which is good because then we don't have to deal with double triple bond anomalies. But the double bond and the OH group now have higher priorities. You start numbering at the highest priority group. So it makes the numbering scheme easier. So if I look at this, I see an OH and a double bond. By definition, the OH gets carbon number 1. It's higher than a double bond. Now, do I go clockwise or counterclockwise? Well, in this case, I've got a double bond, so I have to go clockwise so that the double bond now gets the lowest number after that. So you start at the highest priority group and then number it. Either if there's another priority group, it gets the lowest possible number, or if there were no other high priority groups, then you would just number to get the first substituent the lowest number. And if there was a tie in that, it would go to alphabetization. It always goes to alphabetization as a tiebreaker, eventually. So in this case, this is a cyclohex. The OH group has the higher priority, so it comes last. So this would be a cyclohex 2-ene, and then 1-ol. Do I want to go here or not? Number one, the one is optional, because when you have a cyclohexene-ol, it's understood that the OL group automatically has to be number 1, so you may not see the 1-ol because they assume it's automatically number 1. You can put it in. I'll put it in just to avoid the confusion for the moment, but it may not be there. And if it's not there, they've decided that you can't have an E next to an OL. So if that wasn't there in your book, you would see this as a cyclohex 2-ene-ol with no ene, with no E in the ene. So you might see it that way, which just means double bonds between 2 and 3, and by definition, the OH group has to be number 1. That's what it means. Okay. Either way, 4-methyl cyclohex 2-ene-ol, 1-ol. So I just put the substituents in. Do I have to say cis or trans? No. With these rings, the double bond doesn't really have a cis or trans. It's always going to be the ring carbons are always going to be cis, because I can't make a ring otherwise. So that's what happens in the context of the rings. In the context of an alkoxy group, what happens is that it is treated just like any other group. So when I look at this molecule, I have no groups of higher priority, meaning double or triple or alcohols. I have just regular groups, and so now I revert back to I'm going to number this to get me the lowest total sum of substituent numbers, because there's nothing here that automatically gets the number 1 position. And it's weird that they treat alkoxy groups that way, but that's how they do it. So I know this is a bromo. I know this is a methyl. I know this group right here is a How many total carbons? 4, so at least it's a butoxy group. That'll only get you so far, but at least it got you to butoxy. What kind of butoxy? Terse butoxy. Because if you put your finger over the O, that is a butyl group where the attached carbon is tertiary. So terse butyl now becomes terse butoxy. So this is going to be, and terse butoxy, bromo comes before terse butoxy alphabetically. So this is going to be a bromo terse butoxy methyl cyclohexane. The only thing that remains is how do we number it?
Alkoxy, is that one of those groups that, like, in the book they had 2 names for groups sometimes, it'd be like dimethyl.
Yeah. What is that? Let's name this first, and then then I'll kind of. I may have to record. Somebody may want to ask that question, and I'll go through that. But let's name this first, and then I'll talk about all those parentheses names you're going to ignore. What do you want to start numbering at? What group? I want the lowest total sum of substituent numbers. Terse butoxy number 1, clockwise, counterclockwise. So bromine 2, 3, and 4. That gives me a total sum of 1 plus 2 plus 4, which is 7. Can you beat 7? No. So this would be 2 bromo, 1 terse butoxy, 4 methyl cyclohexane would be its name. And again, the terse butoxy is alphabetized on the B because the terse is hyphenated. Okay. So, of the groups for today, they all have low priorities. They all have low priorities, and the trickiest part is how do you handle ethers. But what you're going to find is that in order to be able to name the substituent part of an ether, you need to know your IUPAC, those IUPAC names, the sec butyls, terse butyls, isobutyls, etc., because that's what we can make out of them. I'll record a short video because the question about this group being called a 1,1-dimethyl ethyl group is not in vogue anymore. That is a terse butyl group. There is an IUPAC name for groups that we don't know the common names of that are accepted as IUPAC names, but IUPAC, you cannot have a 1,1-dimethyl group, some people calling it 1,1-dimethyl and other people calling it terse butyl. So IUPAC said, all those parentheses names, gone. We accept terse butyl. Okay. So that's our functional group, or that's those 3. For Monday, there's going to be, I think, 3 or 4 more that we'll go through. I'll send this out. If you want to remember what your functional groups are, we can go over this on Monday as well. Here's a drug. Could you circle the functional groups that are in there? If I circle them, the book circles them. What functional groups are they? And so this is an anti-cancer drug, and it's got a bunch of functional groups in it. And so could we identify which ones they are? So we didn't go over that, but we can do that as well as the naming on Monday. Okay. If you turn in the graded problems, I'll hopefully have those back by Monday. Let's see.